Hey folks, well, way back when we talked about single static assignment forms where when we're going through and recording our expressions, the form A is assigned B op C type of idea, we always use a new unique name for whatever we're assigning to on the left-hand side. And so what we looked at back then was the approach we could use within a single block to go through and say, okay, well, let's pick a name for each of the different variables as we're going through. If the source code reuses a particular name, we assign a new name to replace that reused portion, again, on the left-hand side of our assignments. What we want to take a look at now is where that runs into complications, where we have different blocks feeding into a block and where each of the feeders provide different definitions for a particular variable that we're going to use in the target block. So we'll get into some discussions on that and see how we go here. Okay, so again, the idea is, let's suppose that we've got some variable x that's set in B1 and B2 uses the same name. It sets some value to variable x. Then in B3, we're using x. So if B1 was the one that wound up feeding into B3 on the actual execution pass, then we'd be using B1's value for x. And if B2 was the one that fed into B3 on this particular execution, then we'd be using B2's value for x. Now, if it's gone through and renamed this, so let's say B1 happened to do its renaming and said, okay, well, my x is called x1 now, and B2 renamed and said, my x is called x2 now, in B3, what do we use? We can't use x1 because that won't be right sometimes. We can't use x2 because that won't be right sometimes. We can come up with a new name, x3, but somehow we have to get the value of x1 or the value of x2 into that x3. So this is the problem that we're faced with. All right, so what we're going to do is introduce a new resolve function in our SSA. So this kind of only exists as an abstract concept right now. Somehow we'll have to turn it into code later. But we'll have this idea where we'll say, well, at the start of a block, we'll have it resolve any cases where there's ambiguities like this. So again, if we've got this kind of B1, B2 case we were talking about, where B1 said, okay, my x is assigned a plus b, and B2 said, okay, x is assigned c plus d, and in B3 we said, okay, z is assigned x plus 3. It's going to use whichever execution path led to B3 in this case. So if B1 executed and then passed control to B3, we'd be using B1's x. If B2 executed and then passed control to B3, we'd be using B2's x. So we need some way to resolve that. So we're going to introduce this new resolve function where we're going to say, okay, well, take B1's name for it, which was x1, take B2's name for it, which was x2, and just resolve the two and store whatever the resolved value is in x3, and then we'll go on and in the rest of our block, we'll just use x3. So we're assuming that somehow eventually we'll be able to write code that actually figures out whether we should be using x1 or x2, and then we can just go ahead and use it in the rest of our block. So for what we're going to do for most of this session is we'll go through and look at how we could come up with these resolution points. And then at the very end, we'll look at how we can actually replace these resolves with code in whatever our target language happens to be. So that's more or less where we're going. We should think about when we actually need to do this. Now, it's possible that we've got some block A back at the beginning that feeds through a whole bunch of different paths, and they all wind up at some block B, and some value that's defined in A we use in B. There's no problem there. If that value doesn't get changed by any of the blocks in between, then it makes it correctly from A to B on all of the different paths, and so we can just use whatever that definition is. It doesn't need a resolve. If we've got a name that comes from just a single other block, right? If we just got A feeds into B and there's nothing in between, then we can just use A's name. We don't need a resolve. So there are a couple of cases where we don't need resolution. But on cases where it can follow a value under a name can follow through one path to get to a target node or a target block, and on a different path that same name has a different value, there we need a resolve. So we need to be able to figure out where and when we need to introduce these resolves, and then later on we can figure out how to actually resolve it. So this is the first step. We could just go through and say pretty much resolve everything, but obviously that's overkill. We want to try and come up with an effective approach where we only stick these resolve points in where they're actually needed, or at least try and get close to having the minimal set. We'll actually make some approximations and be a little pessimistic once in a while, but we'll see what we can do to get as close as we can to a minimal set of resolves. I guess the other issue coming up there is if we generate a value in one block and it's never used anyplace else, then we shouldn't be generating resolves for it. Or if it's used up to block B but not after it, then we shouldn't have resolves for that value after that block B. So that's another issue that we want to try and avoid. Because again, we don't want to stick in unnecessary resolves. So just in terms of an example, again, here we've got, let's say block B is our kind of entry point here, and there's two different paths it can take through B1 or B2, and then they both feed into B3 afterwards. And then we'll see in B0, we're going to say, okay, well, A is assigned B plus C, X is assigned A plus C, Y is assigned B minus C. So we get this sequence of computations. And then in the subsequent blocks, B1 makes use of B. So I guess I should back up here. B and C are presumably coming from something before B0, right? So if there was some external item beforehand, that presumably provided our B and C values. So those have to be coming from somewhere above us, if you like. When we get into B1, we're using that same B value that came from someplace outside, and we're also using a D value, which presumably came from someplace outside as well, right? Otherwise, we're using these things undefined. And then we're using the X value that came from B0 and assigning a new value for X. So we're going to need a new name for X in this case. And similarly, we're setting a new value for A, which means we're going to need a new name for A at this point. So B1's going to go through, again, make use of some information that's presumably coming in from somewhere outside, making use of some things from B0, and doing some renaming. So if we were looking at the renaming process in here, we're saying, okay, well, in block A, we had B plus C coming from outside. We're assigning a value for A. I'm going to give it, I could probably have left that at A, but we'll name it A0. And then reuse that local name, right? Keep using the C. Come up with a new local X, a new local Y. And again, all I'm doing here is sticking with whatever name the code originally had and then tacking an index on that just makes it unique. And we'll just increment that index whenever we need to. So in B1, we're going through and saying, okay, well, I've got a new A, so I'll call it A1, and a new X, so I'll call it X1. And we're using the old values for X in the computation. Similarly, in B2, we're going to make use of that same D value that presumably came from outside someplace. We're making use of B0's A value. We're making use of B0's X value. And we're making use of the Z value that we just calculated a moment ago here. So again, we come up with a new name for Z using B's A0 or B0's A0, come up with a new name for W, use B0's X0 and the Z that we just used a moment ago, or we just generated a moment ago. So again, we get this kind of renaming cascade as we go along. Then where things get interesting is where these two things merge and we have to resolve some of those names. So if I say C is assigned A plus Z, well, I need a new name for C in the first place, so I come up with my C1. I'm going to need a new name for A, but we're going to have to figure out which A we're using, which Z we're using, which W we're using, and which Y we're using. Now, we'll take the Y case first. If we look at Y doesn't get changed in either of these things. The Y value that we're using is the Y value that was set back in B0. So that doesn't actually need a resolve. We can just go straight ahead and use it. It's passing through unchanged, if you like. But for A and for Z and for W, Well, what have we got going on? The W, if we came through this path, hasn't been set. So there would have to have been a W defined globally, if you like, somewhere beforehand. Otherwise, we're using the W from B2. Similarly, for the Z value, right? The Z value could be coming from B2. Otherwise, it would have to have come from something before B0. Otherwise, it's undefined. Right? The A value is either the one that was set in B1, or it's one that came through B2 from B0. So again, we've got all these cases where we have to figure out which is the right one to use. Right? For the Z's, are we using the Z from B2 or some global Z? For the W's, are we using the W from B2 or some global one? For the A's, are we using the A from B0 or the A from B1? And so we'll have these series of resolves, and for each of them we'll store them in a new variable of that name. So we'll create an A2 that holds the resolved A's. We'll create a new variable W1 that contains the resolved W's. We'll create a new variable Z1 that contains the resolved Z's. And then we'll use those in the rest of our block. And then here, when we create a new A, we're going to have to increment from the A2, so we create a new A3 here. So this is the kind of result that we're hoping for, is to stick in resolves where we need them, but not where we don't need them. Right? For the variables that we don't use in B3, we don't need resolves. For the ones that haven't changed, that come in identically across all paths, we don't need a resolve. It's just the ones that we use that have actually changed that we need a resolve for. Now, it's also possible that we need resolves for ones if B3 feeds into B4, for instance, and B4 needs something that we haven't resolved here that changed in one of these combinations, then it's possible it will need to resolve that as well. But we want to try and identify what it is we need to resolve and what we don't in a reasonably efficient fashion. So again, there isn't really anything like a resolve function in any of our target languages, so we're sticking it in here as kind of a resolve point, if you like, and coming up with a new variable name for wherever we're going to store it. But sooner or later, we're going to have to stick in actual code that figures out which X should go into X3, for instance, or which A should go into A3. And we want to get an efficient calculation of a minimal set of resolves. It might not be computationally practical to get the absolute minimal set, but we'll aim for a reasonably minimal set that we can calculate efficiently. So we'll kind of flip it around for a moment and think about, if I'm in a particular block and I have some definition, so I say X is assigned, Y, and then some operator in Z, where does that X get to? Which subsequent blocks change X? Which ones kill my value of X? Which ones use X before it gets killed? And where's the last point where my X actually gets used? Right? Those are the interesting questions that we have to try and answer, because those are the ones that are going to dictate where this thing might flow to. How far do I need to keep track of this? So we're going to go back to that idea of dominating nodes, and we're actually going to come up with a whole new suite of definitions here. We'll look at dominating nodes, dominating sets, dominance trees, and dominance frontiers as kind of intermediate steps to walk us through to get to an algorithm we can use to figure out where we need to put these resolve points. So, if you recall, what we talked about before was a dominating node is one that lies on every path to some target point. So you have to get through that, you have to go through that node to get to wherever your target node is. Just a note in terminology, because I'm terrible about this. I'm pretty much, as we go through this, I'm thinking of our control flow graph as having a bunch of nodes, each of which represents a basic block. So I'm going to keep switching back and forth between saying node and saying block and using them pretty much interchangeably, because mentally I'm thinking of them interchangeably. Our nodes are just representing blocks. So if I swap back and forth, that's what's happening, and I apologize, but I just can't seem to break that habit. So in terms of our definitions, so I think in the definitions we used a couple of weeks back, we talked about the dominating set for a node being the things that dominated it. We're going to flip that around right now and look at which blocks or which nodes are dominated by some block B. So I'll try and keep that clear and use dom by for this. So if n is in dom by B, then B is on every path to n, right? To get to n, you have to go through B first. And we're always thinking of this in the context of our control flow graph. So there's always some entry node, B0 or whatever you want to call it, some entry node. And we're thinking about all paths from that entry node to whatever our destination is. So if we think about it in terms of our definitions and whatnot, then any definition that we make in B is valid, exists along every path to n, unless something in between actually changes it. So as far as B is concerned, I'm going to assume that my value flows through to every place that I dominate, unless somebody in between explicitly takes a step to change it, in which case they can worry about telling n about any resolves that have to take place. So I'm not going to request resolves in any of the blocks that I dominate. Where I'm going to look at adding requests for a resolve are places where my stuff gets to, but isn't the only path to. So nodes that are kind of reached from my dominating set here, but that I don't actually dominate. So we'll take a look at where we can use this dom by and where we're leaving the dominating or the dom by set for B. And this is where we get into the notion of dominance frontiers. So if I've got my block B and I've got this set of nodes that it dominates, then the dominance frontier for B will denote DFB. And we'll say a node is in that if X is in dom by B, Y is not, and there's an edge from X to Y. So this edge kind of marks the transition where we're leaving the dom by set of B. So the frontier are the nodes just outside the set that's dominated by B. So if we've got a block B and a block Y that's in this dominance frontier, then any definition that's made in B could reach that other block, but it's not the only way to reach that other block. And this other node is just outside. It's kind of the first point that we encounter that's not in the dominate by set of B. So these are the points where we'll ask for a resolve function, is that those nodes in the dominance frontier of B are the places where B will say, you're a point where I'm providing a value that might need to be resolved. So if we can figure out these dominance frontiers, then we can come up with an effective way to start inserting resolves. So if we think of this in terms of an example, let's say this is a chunk of some bigger graph, and we're looking at this little set here. Let's say if we look at A dominates B, C, and D, right? You can't get to B, C, or D without going through A first, right? There's another way into F, there's another way into E, but those three nodes A dominates. So they're in dom by B, if you like, or dom by A. That should be a dom by up there. So those three are in dom by A. But when we make that transition from D to F, there's another way into F. So if I defined some value in A, say I defined X, then when I got to F, there is presumably another way to define X. Well, if F actually uses X, there'd be another way that the x could be set. So here I would need to resolve x. Similarly, if I define my x in A, then when I left C and went into E, I would have to resolve that x, because presumably there would have to be some other way for the x to be set coming into E if E is actually going to make use of x. Right? So again, these transition points where we're leaving the set that's dominated by A, those are the points where we have to stick in our resolves. So this is where we're heading. So we want to find this dominance frontier for any given node or for any given block. And the blocks that are in that dominance frontier are the blocks where we're going to say, could you please stick in a resolve for me? Later on, we'll have to look at trimming that, pruning it a little bit to avoid making unnecessary resolve requests there. Again, if I define an x and it's never used by anything from in the dominance frontier or afterwards, then there's no need for a resolve. But for the moment, we'll just identify them first. So what we're going to do is kind of explore the tree out of B, identifying what's dominated by B, and then identifying the paths, if you like, that leave that tree. So if we thought of our previous example here, we'd have this tree of A going to B and to D and to C. And then, if you like, the other elements are leaving this little subtree. So that's what we're interested in, is exploring the tree from A, figuring out what's dominated by A, and then figuring out where we're leaving that tree. And again, it's basically amounts to a bunch of path exploration here. So we'll introduce a new term here, just because we haven't introduced a new term in almost a whole 2 minutes. So this will be an immediate dominator. So the idea is B is node's immediate dominator if B dominates N, and if it's the last thing that dominates N, if you like, the immediate predecessor, or as far as dominating nodes go, the immediate predecessor. There is no dominating node between B and N. So what we're going to do is simplify our graph when we go through this to look at just the immediate dominators, and this is going to be our dominator tree. So let's take a look at a bit of an example first. So again, suppose we had this as our control flow graph. Then A dominates everything in here. D dominates E and F. And if we were looking at immediate dominators, well, for F, what's its immediate dominator? It's the thing that dominates it that comes most recently, if you like. So it's D. Right? There's nothing between D and F that dominates F. Right? E is along one possible path, but only one path, so E doesn't dominate F. So the immediate dominator for F is D. If we look at E, again, the immediate dominator is D. It's the thing right before it, and it's on all its paths. For D, the immediate dominator is, again, the most recent thing that is a dominator, which is going to be that A. Right? B and C can't be it because they don't dominate it. They don't lie on every path to D. And so A is the immediate dominator for D, and similarly for B and for C. Right? You can't get to either of those without going through A, and it's right before them, so it's going to be the immediate dominator. So again, you can come up with the immediate dominators logically in a fairly straightforward fashion. If we go through and produce the dominating tree, what we'll do is list each node that's an immediate dominator and which things it is the immediate dominator of, and we'll build it out that way. So let's take a look at, again, just a sample control flow graph and what its dominating tree might look like. So let's say we've got this, where we've got B0 leads into either B1 or B2, B1 can lead into B3 or B4, B4 and B3 both feed into B6, B3 also goes into B5, B2 and B6 feed into B7, and so we've got this, a few different possibilities going on here. So in terms of the dominating tree, well, B0 dominates everything. If we take a look, B0 is obviously going to be the immediate dominator of B1 and B2. So B1 and B2 are obvious cases here. if we keep going through this, B1 is going to be the obvious immediate dominator for B3 and B4. Right? It's right before it, and it's a dominator for it, so that's pretty clear. For B5, again, B3 is a pretty obvious immediate dominator. For the other ones, the points where you've got convergence, it's a little bit more interesting because you have to go back and find the point where the paths diverged, if you like. So for B7, what's the most recent dominator that lies on every path? Well, the dominator for it that's most recent. Well, the only thing that lies on every path to B7 is B0. So B0 is the immediate dominator of B7. For B6, what have we got? Well, for B6, you've got B0 and B1 are its dominators. B1 is the most recent one, so B1 is the one that we're interested in. B1 is our immediate dominator. So we get our B0 is the immediate dominator of B1, B2, B7. B1 is the immediate dominator of B3, B4, B6. And B3 is the immediate dominator of B5. So this is the dominating tree that we'd be interested in. So if we wanted to look at the dominance frontier for B0, for instance, we'd be looking at any edges that leave this tree. Similarly, if we wanted to look at the dominance frontier for B1, we'd be looking at any edges that leave this subtree. So if we can produce this dominating tree, then we can just look at edges that are leaving it pretty much and figure out what the potential resolve points are. So in terms of looking at this, again, for our dominating tree, if you take a look at it, every node's parent is its immediate dominator. And you can kind of work backwards if you like. If I'm looking at any node in this, all of its dominators are on the path going back from it. So what we're going to do is use that dominating tree to compute the frontier for each node. Once we've got that, we'll use it to figure out where we're going to place the resolve functions. Once we've got that, we'll look at what we need to do to carry out the actual renaming. And once we've done that, we'll take a look at what we need to do to actually replace that with target language code eventually. So for computing the frontier from the tree, what we'll do is come up with a dominance frontier for each individual node. So we're going to compute kind of all of these things in parallel. And initially that's just going to be empty for each of them. And then we'll go through each node and looking at the control flow graph. If the node has multiple predecessors, then what we'll do is look backwards through each predecessor, and we'll work our way back looking for the immediate dominators of those predecessors. So we'll look at the immediate predecessor, or the predecessor of n, and we're going to kind of iterate back from there. We'll say, well, that's not the immediate dominator of P, we'll work backwards, add n to the dominance frontier for that, and move back a step. Look at the immediate dominator of the node that we're currently on. So we're going to work backwards up the tree, figuring out where we need to keep inserting things. So if we just take a quick look at our example from slide 12 here. So we'll take a look at B7. Right? So for B7, we had this one feed in from B2 and this other feed that came from B1, B3, B6. And in that dominating tree, we had our B7 just had its immediate dominator as B0. So for predecessor B, right, okay. Sorry, confused myself for just a second. I didn't think B2 was the predecessor of B7, but yes, it is. We've got B2 or B6. So for predecessor B2, right, we assign I to be that predecessor. It's not B0, B7's immediate predecessor, so we add B7 to the dominance frontier for B2. And then we set I to its immediate dominator, which from that tree is B0, and at that point we stop, right? We're going through looking for the immediate dominator of B7. Then we go through and do the same thing for B6, right? We look backwards. Well, we set I to be its predecessor, B6. That's not B0, it's not our stopping point. So we add B7 into the dominating frontier for B6. Then we go back and say, okay, well, let's set I to its immediate dominator, which is B1, right? B1 is the immediate dominator for B6. That's not our stopping point, it's not B0, so we add B7 to the dominating frontier for B1 and set I to B1's immediate dominator, which is B0, which is our stopping point. So again, if you look back at our set here, we were going through and saying, okay, let's look at B6, look at its immediate dominator, which is B1, right? And we're going through and trying to decide which things B7 is leaving the graph of, right? So we are leaving B1's graph, right? If you look at it logically, we're taking a look at B1 dominates this little set of 5 nodes here. If we leave that little set of 5 nodes, we need to potentially add a resolve, which is what we're recognizing here, right? The node from B6, or the jump from B6 recognizes that we need B7 in the dominance frontier for B1. Similarly with the B6 one, right? If we look at B6, it's, it pretty much just dominates itself. So when we leave it, we're hitting a potential resolve point, and we need B7 in the dominance frontier for B6. And we don't need B7 in the dominance frontier for B0 because B7 is part of B0's dominance tree. So this does actually flow through and give us the results that we want, recognizing when we're still outside the dominance tree for something and when we've entered the dominance tree for something. All right, so if we can manage to go through and identify all these dominance frontiers, then we can go through and say, okay, well, for B, anything that's in its dominance frontier is a place where we might need to request a resolve function be added for any of our definitions. Now, they don't need to be there if the definition that we provide is never actually used in N or any place after N, but this is one of our potential targets. So what we'll do from the compiler perspective is say, well, let's figure out what names get generated in one block and used someplace else. So if you think about the list of upwardly exposed variables, the variables that a function or that a subroutine uses or a block uses that were defined before the block someplace, where we're using it before we define it, before we set a value in it. Those upwardly exposed variables, if we take the union of all of those are the set of all the different names that must be defined someplace outside the block where they're used. So that would give us a target list of names, right, of all the possible names that we might want to do a resolve on. If something's not in that, we don't need to do a resolve in it because it's not getting used by anybody afterwards. So that can give us a first kind of prune, if you like. So what we'll do is take a look at this set of names and take a look at which names are defined by which blocks. And we'll use that to see if we can do some reasonable placing of our resolve functions. So that does mean that first we have to figure out what all the names are and which blocks define them. So we'll come up with a list of all the names, and we'll come up with a list of all of the definitions, which blocks define which names. So defs I will be a set of all of the blocks that define I. And we'll just expand this as we need to. Add new i's to it as we need to, and add new blocks to the set for I as we need to. So what we'll do is go through each of the blocks in sequence and say, okay, well, let's identify which things are killed in that block, and then go through each operation in the block and say, okay, let's say the operation is of the form, and again, we'll just stick with the binary form for now. Let's assume we've got something that's x is assigned y op z. Then if y isn't in var kill, so if it's not something that we've killed yet, If it's not something we've redefined yet, then it needs to be added to that name set. Similarly for Z, if we're using Z but we haven't set a definition for it inside the block yet, we need to add it to that names list because it must have come from someplace before. X is something that we just assigned a value to, so we'll put X in varkill, right? Because now inside our block we've come up with our own local definition for it. Now, if X isn't something that we've seen before, then we'll add a definitions set for it, and we'll add B to that definition set. If it is a name that we've seen before, then we'll just add B to the definition set for X. Right? We're saying B, our current block B is one of the ones that can define X. So that's how we're going through and generating our list of names, our global collection of, if you like, shared names that are shared across blocks, and our lists of who sets values for each of the different names that are used. Now, this isn't taking care of any sequencing information. This is just kind of across the board, which names are used, or which names are used across blocks, and who could possibly set them. So there's no flow information being used here. Then for adding the resolve functions, what we'll do is go through each of the names in that list. We'll get the set of blocks that define that name, and then for each block that's in there, we'll look at its dominance frontier, and for every block that's in that dominance frontier, we'll say, if there isn't already a resolve function for that name in that block, then please add one. And while you're at it, add that block to the list of things that we should be processing. So here we're going through and trying to figure out all of the places, for each name that could be shared. We'll go through all of the places that define it and find all of the places where our definition of it might clash with somebody else's. And that's essentially the sequence we're going through here. Now, we could make this a little bit more efficient if we added an extra test in here to make sure that V is actually still alive at this point. But that's an optimization issue for another time. All right, assuming that we've actually gone through and done this, assuming we've actually gone through and figured out all of the different resolve requests that we need to add across all of our different blocks, then we should think about the naming process that we're using here. I mentioned earlier that typically what we'll do is take the base name, the A, the X, the foo, the whatever it happens to be, and just add an integer to the end of it. So foo, and even if the name had an integer in it already, we're just adding yet another. So if it was, foo123, now it's foo1230, or foo1231, or foo1232. So we'll have a counter that keeps track of which values we've used for that base name so far, and we'll just bump it up every time we use one. And what we'll also do is for each of the base names, we'll keep a stack that's keeping track of which ones are actually in use right now. So as we generate a new name, so when we generate, A0 or A1 or A2, we'll push it onto the stack. And when we exit the block that we defined it in, then we'll pop it off the stack there. So we can keep track of which ones are live right now. Alrighty. Finally, we need to take a look at how we're going to take these resolve functions and replace them with actual target language code. So here, we need to figure out, if you think way back to the beginning where we had, block 1 fed a value X into block 3 and block 2 fed a value X into block 3. If we get the actual sequence during execution where we do block 1 and then block 3, as we transition from block 1 to block 3, we want to assign block 1's value for X. If we're taking the other path, as we transition from block 2 to block 3, we want to assign block 2's value for X to whatever the target variable is called. So what we would be doing is going through our control flow graph and saying, okay, where I see an edge, well, let's say we've got block M produces a value for x that it's labeled xi, x0, x1, x2, whatever it happens to be. And another block has produced xj, right? X with some extra label j. And in the target, right, in the block that we're both feeding into, we have this, xk is assigned resolve I and j. What we want to do is say, in our control flow graph, when we go from block M to our target block, we want to insert the extra assignment statement, xk is assigned xi. Right? We want to do that extra copy. On the other hand, where we follow that edge from block N to our target block, we want to introduce the other copy statement. Right? So you're just introducing copy statements from the block you're leaving to the block you're entering. And this is the kind of the key point for our translation process. But again, that's something we can worry about after we've gone through and figured out where we actually need to do these resolves. All right, lots of fun. So that is, I think, most of the key stuff that I want to take a look at for the single static assignment form, the last kind of major issues we want to touch on. What we'll do next time around is get into a little bit more of the whole program optimization and a few other optimization techniques and see where we can go from there. All right.